We did differentiation last lesson, and so the obvious next step is integration, okay? Now, integration of inverse trig functions properly, it needs integration by parts, okay? So this is not integration of inverse trig functions, it's integration that leads to inverse trig functions, okay? So let's start with the statements about derivatives that we know. For instance, the derivative of sine inverse. Do we know it by now? It's a fraction. It's 1 over the square root of... When am I going to learn my lesson and stop asking you questions like this? Okay, good. Now, before we move on to that, I want to look at some very common variants of this, okay? Dipping into what we know about chain rule. Okay, so for instance, if I slap a coefficient on the x, okay, for instance, let's think about inverse sine of ax, okay? What difference does it make? Well, you're going to have the derivative of the inside, right? So you've got your a, yes? And then you've got your square root of 1 minus a squared x squared, right? Okay. Now this tends to be, well, I mean it's true, but it's not all that useful and it's not particularly neat. What you'll see far more often is when you put that coefficient on the denominator. Now usually you're like, well, that would make things ickier and messier, wouldn't they? But in this particular case, as you'll see in about 30 seconds, it actually works out quite neatly. Watch. What's the derivative of the inside function? 1 on a. I'm going to chuck it in brackets since I've got fractions on fractions here, right? So therefore I've got this 1 minus, and I'll have all of this squared, x squared on a squared, won't I? X squared on a squared. And now you can see why that 1 on a is actually very useful, right? It's going to go down to the denominator, number 1, and then when it comes inside underneath the square root sign, it's going to become an a squared, isn't it? Right? So that's why you'll get this, a squared, and it just very neatly cancels with the x squared on a squared, okay? So, all of these make statements about integrals. They're all derivatives, they all make statements about integrals. This one tells you, color, okay, this one tells you that the integral of 1 over the square root of 1 minus x squared, right, with respect to x, is sine inverse plus a constant, okay? In the same way, this one tells you this, integral is sine inverse of x on a. Okay? So this time, going straight to the integrals, right? Let's think about tan inverse, because that looks a bit different to sine inverse, doesn't it? Okay? What would be the integral that I'm interested in to end up with tan inverse? It's going to be 1 on 1 plus x squared, that's just my regular one, dx, okay? That's going to give me tan inverse plus a constant, okay? Now, I want you to think for a second, what if I wanted something like this? If I wanted to take a coefficient into account, and I wanted it to cancel nice and neatly like I have here, okay? Can you tell me, why can't I simply say, have, if I want to end up on this, a squared plus x squared, okay, with respect to x. It's not going to be simply chucking a over a inside here. Can anyone see why? It's not going to be equal to this. What's the problem? Why can't I do the same thing with tan inverse that I do with sine inverse? Think about what exactly made it cancel in this case, right? This 1 over a goes on the denominator, because it's a fraction, and then it comes under here and it becomes an a squared underneath the square root. So, perfect, okay? Aha, but when you've got this equivalent thing for this, right, it's not going to become an a squared on the denominator. Why not? Because there's no square root sign there to convert it into an a squared, okay? So in order to make it cancel out nicely, like this, you need an additional 1 over a out the front, okay? If you want, I can prove it to you. Okay, let's differentiate. 1 over a tan inverse x on a. Okay, what's going to happen? Well, 1 over a derivative on the inside on the top. 1 plus x squared on a squared down the bottom. And then, of course, I have this constant floating out the front. 1 over a. Okay? That 1 over a and that 1 over a, they become the 1 over a squared. And that's how it cancels. Okay? Are you content with that? Now, I've done sine inverse, I've done tan inverse. I did that very deliberately because wake up. Those results and those results only appear on our table of standard integrals. Okay, now it's a bit hard to see from there. So when this thing wakes up, it will show you the relevant parts. And you'll see that we've got our, what am I looking at? It just gives you this form and this form.
They got rid of the sign, right? They got rid of the sign. What the Oh yeah, can you get there?
Where was I? Okay, can you see what I'm looking at? Right there in the middle, okay? So there's tan inverse and there's sine inverse. Now, there is a conspicuous absence there, isn't there? Where's cos inverse? The answer is cos inverse is there. He's just hiding, right? Because when we think about integration, right, and that's what these are, they're not standard derivatives, they are standard integrals, okay? Because they're indefinite, simple example, right? When you integrate a function, you don't just get one primitive back, you get a whole family, right? All of the guys who are on top of each other, but share the same gradient, because that's what this is, right? So therefore, when you think about the result for sine inverse, okay, which is, it's the A one, isn't it? So you got this. Okay. Because you are not just getting one primitive, you're getting the whole family, right? Cos inverse is in here. He's just hiding, right? What does sine inverse look like? Looks like this, right? What does cos inverse look like? He looks like this, right? But because I've got the whole family of these guys, right? I have this guy and I have this guy. Now, have a look at him. What's the difference? It's just been turned around, right? So comparing this guy and this guy, sorry, I think you're thinking about the difference between these two. They're shifted. But think about the difference between these. One is being flipped, right? In this case, the one I've drawn, it's being flipped this way, horizontally, right? But if I choose a different constant, for example, if I put him down here, see that? Now if I compare this, let me put it in a different color up here. I put him here, now he's been flipped vertically, right? So I can just as easily say this is negative cos inverse. Just it's a different constant, that's all, okay? So it's not that they're being discriminatory, it's that cos inverse really is actually there, okay? Because the relationship with the derivatives is so similar, okay? So, you need to be very familiar with, I should circle them for you. This result here, and I didn't even write it on one line, did I? This result here, okay? Which is why they're on your table of standard integrals, okay? That's really more of a, it's kind of a safety blanket. You shouldn't need to look at those, but you have to be careful. They're quite easy to mistake, aren't they? Okay, so be careful.